My name is Victoria Paneva from the University of Bayreuth, and I will present OptiTrap, optimal trap trajectories for acoustic levitation displays. Acoustic levitation allows us to create volumetric displays that present midair content in real physical space that can be reached into. Now, the problem of how to control this dynamical system as to follow a predetermined shape was largely unsolved until now. In this paper, we present an automated pipeline that produces physically feasible, time-optimal control inputs that allow the rendering of generic volumetric content on acoustic levitation displays. An acoustic levitation display normally consists of two opposing arrays of transducers emitting ultrasonic waves. A particle, which is a millimeter-sized expanded polystyrene bead, is trapped in a twin trap using focused ultrasound. By generating the acoustic trap at different positions in the display volume, we are able to steer the particle in any direction. But the display still shows only one volumetric pixels. Now, in 2018, Smalley et al. Presented a microscale image in real space. Laser light was used to trap a cellulose particle in midair that reveals a shape within 100 milliseconds, that is, within the integration interval of human eyes. A year later, Hirayama et al. Showed that a similar effect can be obtained not only with optical but also with acoustic trapping, and this opened an avenue of new possibilities for multimodal acoustic levitation. That's pretty exciting, but how do I generate a specific shape on the acoustic levitation display? Well, until now, you could only rely on trial and error to find physically feasible trajectory resembling your intended target shape, which understandably is a time-consuming and challenging process. To provide a structured algorithmic solution to this problem, we need to solve two main challenges. Challenge 1 deals with determining the path timing. The display input information typically consists of a path geometry without any timing information. That is, we only know where the particle should be, but not when. And the content creator needs to come up with a timing strategy. The timing strategy is very important as it affects the velocity and acceleration applied to the particle and hence on the physical feasibility of the content. The paths in the video contain around 1,000 traps, but only single infeasible point results in the particle being ejected, like when approaching a sharp corner too quickly. Challenge 2 deals with the exact positioning of the acoustic trap. The figure visualizes the force field when a trap is generated at the center. A particle at the trap location is held in place because of the zero net force. If we now move the trap location, the force field changes and the particle can move. However, where exactly to place the trap is not intuitive. Previously, the traps were placed on the path to be rendered. This placement is suboptimal and only works for low frequency. As we can see in the figure by Fushimi et al., as the rendering frequency increases to 5 and then to 10 Hz, deviations from the intended shape become more apparent. The method that we propose accepts a reference path, the shape of the heart in this case, as an input without any timing information. It then takes into account the capabilities of the device and its trap particle dynamics and combines this with a path-following approach. As an output, it produces feasible trap trajectories determining both the position and the timings of the trap. Note that the trap positions do not lie on the reference path. These are the black dots in the figure and the reference path is the gray outline. Finally, the resulting particle motion is executed on the actual device. So while previously feasible trap trajectories needed to be tuned manually for each shape and levitator, relying on trial and error, OptiTrap is the first structured numerical approach that produces physically feasible and nearly time-optimal trap trajectories for levitation displays. It automates the content creation process by allowing for a systematic exploration of the range of contents that a given levitator can achieve. And finally, it supports complex shapes with sharp edges and significant changes of curvature. Next, I describe the two stages of our approach, starting with the mathematical model of the trap particle dynamics. The trap particle dynamics of such systems can be described by simple Newtonian mechanics, where P denotes the particle position, P dot and P dot dot the velocity and acceleration of the particle respectively. U is the control input specifying the position of the acoustic trap, M is the particle mass, and F the net force acting on the particle. Previous studies have shown that the particle is mostly driven by the acoustic force, so we omit other forces such as drag or gravitation in our analysis and look for a suitable way to mathematically describe the acoustic force. The acoustic force acting on a small spherical particle in the far-field regime is usually described in physics using the Gorkov potential, which we take as ground truth in our analysis. The figures show the distribution of the acoustic force when a trap is generated at the center. The two colors correspond to forces acting in the opposite directions. Note that the Gorkov model becomes increasingly more complex away from the main trap. But our specific setup and objective allows us to consider simplified analytical models that provide a good approximation for the region around the peak forces. Previously, spring models with a stiffness parameter K were used for this purpose, but they are one-dimensional. That is, the force in X only depends on the trap particle distance along the X-axis, so they are only valid for a small area around the trap along the main axis. Sinusoidal models with amplitude A and frequency V provide a better approximation, but they too become inaccurate at points deviating from the main axis. So, we observed that in the region of interest, the forces distribute mostly axis symmetrically. Hence, we can approximate the force as follows, where AR and AZ denote the peak forces along the radial and vertical directions of the trap respectively, and the V parameters are the characteristic frequencies of the sinusoidals describing how the forces evolve around the trap. In this way, we obtain a model that considers the trap particle distance along all three axes, and we obtain a much better force approximation in the region of interest. Now that we have a sufficiently good model of the forces, we move on to the computation of optimal timing. We define the reference path as an explicitly parametrized curve. The parameter theta models the progress along the path from the starting point θ0 to the endpoint θ final. To create the persistence of vision effect, we consider periodic paths, so we set the starting and end position and velocity to be the same. We assume that the particle follows the reference path Q exactly at all times, and we use a virtual function V to control the progress of the particle along Q. So we model this timing law as a double integrator in order to avoid large jumps in the acceleration. We minimize the total time t it takes to render the shape, And in the cost function, we also add a regularization term that smoothens the trap trajectory to avoid too aggressive solutions that could potentially destabilize the particle, like the example in the figure. The cost function is subject to the following constraints that ensure the particle remains on the prescribed path and that it admits the dynamics of the modeled trap particle physical system. Lastly, we discretize the final optimal control problem and we solve the resulting nonlinear programming problem using an appropriate optimization solver. Finally, we evaluate the performance of our algorithm and compare it against other approaches in 3 main tests. We use 4 test shapes for the evaluation. The circle is selected as the trivial case to test whether our solution really converges towards the optimal. The cardioid and squircle represent simple shapes featuring sharp corners, and we select the fish as an example of a composite shape featuring corners, straight lines, and curves. The first condition we take is the current state of the art in the literature, which we take as a baseline. It uses homogeneous sampling of the path parameter and it places the traps along the reference path. We compare the baseline against our approach, which considers feasibility and trap particle dynamics and deals both with the timing and the trap placement challenges. So first we investigate the maximum size that can be achieved in persistence of vision time, that is 100 milliseconds or a rendering frequency of 10 Hz. For the cardioid, we get a size increase of 12.9% using our approach, and the result is similar for the fish as well. The most striking difference is the one for the squircle of 562.5%. And second, we investigate the maximum rendering frequency while keeping the size constant. As expected, we achieve the same rendering frequency for the circle with both methods. We obtain a 25% frequency increase for the cardioid, 150% for the squircle, and 11% for the fish. Note here that while for our approach, we automatically get an estimate for the feasible frequency, for the baseline we had to test many different frequencies on the levitator to find the maximum feasible one. And the workflow was the same for the maximum size test as well. Finally, our third evaluation test is an ablation type study. We name OCP timing an approach which makes use of our OptiTrap algorithm to compute optimal and feasible timing, but still positions the traps along the reference path. And we compare it against the full OptiTrap approach. This helps us to investigate the importance of this portion of the algorithm for the end result. We compare the reconstruction accuracy with both approaches using optical motion capture. And we obtain a 21.3% decrease in the root mean square error normalized by the total length of the path for the cardioid and 60.5% for the fish. In summary, with OptiTrap, we introduced a novel multidimensional model of the acoustic dynamics and formulated and solved a nonlinear path-following problem, taking into account the system dynamics. This made the rendering of complex shapes not demonstrated before, such as the cat, possible. We also provide a solution to a problem that has not been properly addressed before, of how to transfer a particle into a periodic orbit from rest and vice versa, and also how to achieve controlled, smooth transitions from one shape to the next. Thank you, and for more details, please check out the full paper.